This is what I'd say a slightly hard topic for some people. So let's go into depth on what the formula for binomial distribution is, its definition. We're going to look at each stage of what of the formula, and we're going to look at what they all mean by themselves. We're going to look at examples, and at the end we're going to look at a question, and we're going to do that one together. Okay, so first for a definition of the formula for binomial distribution. So we use the formula for binomial distribution to find the probability of k successes in a finite number of trials n. Okay, and this is especially important because there are actually a couple of rules that you need to know for binomial distribution. So the first rule, there have to be a fixed number of trials. So if I'm flipping a coin, I have to flip the coin 6 times. Okay, has to be a fixed number of trials. It can't be that I'm doing it forever and ever, or I don't specify the number of trials. Okay, has to be specified number of trials, or a finite number of trials at the very least. We also have to have 2 possible outcomes where one is a success and one is a failure. So for example, if I roll a die, my success would be getting a 6, and my failures would be getting a 5, a 4, a 3, or 2, or a 1. Okay, has to be 2 possible outcomes, hence the name binomial distribution. I also have to have a fixed probability of success, and the trials have to be independent of one another. What these mean is that the probability of success has to stay the same, and that the trials don't affect each other. So if I flip a coin, if I got heads on one coin, that's not going to affect the probability that I get heads on the next coin, and we treat each trial as being independent. Okay, so now let's look at the formula for binomial distribution and what all these terms actually mean. So here we have the probability. So the probability that the x, which is a random variable, is equal to k, which is the number of successes, n, which is here and here, that's the number of trials, hence we need a fixed number of trials. P is the probability of success, and if we have defined P, N, and K, we can also find the probability of failure as a probability of failure plus the probability of success should equal 1. So the probability of failure is 1 minus P, and the number of failures is N minus K, because if you have 2 possible outcomes, which are failures and successes, well, that means that the number of failures plus the number of successes should equal n, which is the number of trials. Okay, so now that we've gone over what all these terms mean, let's go into the first part, which is n choose k. So this is actually covered in another part of the A-level syllabus in pure maths, which is the binomial coefficient. This is known as a binomial coefficient. So we have n factorial over k factorial times by n minus k factorial. So what does this all mean? So let's say I flip a coin and I want to get 2 heads, which means that to get 2 heads I need 1 tail. So these are all the possible outcomes I can get for flipping a coin 3 times. I can get 3 heads, 2 heads, 1 tail, heads, tail, heads, tail, heads, heads, tail, 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 heads, tail, heads, tail, heads, tail, tail. Okay, so the first part of the binomial coefficient, that's n factorial. Okay, this lists out the number of successes I could have in getting 2 heads, 1 tail. But there's a catch to this, because if we model each head's as being a distinct successful outcome and tails as being a distinct failure, then what we could end up is a scenario where we have H1, H2, T1, H2, H1, T1. But we don't care about whether the one we've assigned to this H is here or here. We just care about if it's two heads, one tail, heads, tail, heads, or tail, heads, heads. That's all we care about. So what k factorial and n minus k factorial do is that they get rid of this, okay? And we're just left with this. And when we do n factorial over k factorial times by n minus k factorial, we should end up with only this for our total unique outcomes for successes in n trials, okay? So k factorial, that's just the number of ways we can rearrange heads within this, okay? And then n minus k, well, that's just the number of ways that we can rearrange tails in this. Okay, now we only got one tail, but in more complex examples, there might be two tails. Okay, so this part, all this means is that this is just our total unique outcomes for success in n trials. Now we'll move on to the other part. So now that we have our total unique outcomes for successes in n trials, we need to figure out the probability of getting these unique outcomes for successes in n trials. Okay, so now we're going to go back to a little bit of GCSE, a little bit of earlier maths revision. Okay, so starting off with a simple example, if we flip a coin 5 times, right, and we get one heads, and we get 4 tails, right? We can find the probability of getting 1 heads and then 4 tails, and we can just model this as 0.5 to the power of 1, okay, because that's just 0.5, that's the chance of getting heads, times by 0.5 to the power of 4, as chance of tails is also 0.5. So we notice how heads, that's our success, 1 heads, that's our success, 4 tails, that's our failure, right? So we do 0.5 to the power of 1 times by 0.5 to the power of 4 to get the probability of 1 heads and 4 tails in this arrangement, okay? So we can also represent the probability of success, P, as being 0.5, that's probability of getting heads, timesing that by the number of successes, so our number of successes is just 1 in this case, so it's going to be 0.5 to the power of 1, times by 1 minus the probability of success, so the probability of success is already 0.5, so that'll just be 0.5, times by n, which is the number of trials, minus k, where k is a number of successes. So that would be 5, so we flip the coin 5 times, minus our number of success, 1, which is 4. So that's, in essence, what this part actually means. So when we put it all together, we get the probability of we can get a probability of k successes in a finite number of trials, n. Okay, so that's the probability of success times by to the power of the number of successes, okay, and then that's the number of, and then 1 minus p is probability of failures to the power of number of failures, right? Because we've seen those were our number of failures, okay, that was a number of success. Okay, so now let's move on to a question, and maybe you'll hopefully understand this a little bit better. So the probability of a light switch being faulty is 0.08. We take a sample of 10 switches and we want to find the probability that the sample contains 4 faulty switches. So now we have to see if it fits in with the rules that we determined for binomial distribution. Okay, so are there a fixed number of trials? Well, let's see, there's 10 switches. Okay, we take a sample of 10 switches. Okay, so there are a fixed number of trials. Are there two possible outcomes? We can either have faulty and not faulty. So in this instance, we model faulty as being a successful outcome. So yeah, yes, there are two possible outcomes. Is there a fixed probability of success? Yes, so the probability the light switch is faulty is 0.08. So, and that doesn't change. So yes, we can say there's a fixed probability of success. Trials are independent of one another. Well, we infer that because the probability that one light switch is faulty will not affect the next one in being faulty. So we can write this as where 0.08 is our probability of being faulty and 10 is our number of trials. Okay, so let's put this in the formula. Okay, so we have 10, we have 10 factorial over 4 factorial, okay, because that's our successful outcome, minus times by 10 minus 4. Okay, because if we have 4 faulty switches, that means we have to have 6 working switches as well. Okay, and we times that by probability of success, that's 0.08 to the power of our number of successes, which is 4, times by 1 minus 0.08 to the power of n minus k, which is 10 minus 4. Okay, because we've had 6 failures. And that should give us an answer of 0.0052 to 3 significant figures. Okay, so that's all for today. I hope you found this useful, and if you have any questions, I'll be happy to answer them in the comment section.